We're not going to quite get this far today, but we're going to be more than halfway there. This is the big goal. Now, I don't know if you can draw that well, but the idea is we'll be able to name these shapes. We'll be able to take a molecule and be able to predict its shape. And so to predict the shape of something so, you know, a millionth of the size of a hair is pretty spectacular, but every molecule has that exact same shape of that compound. So it really conglomerates into the properties. I mean, the boiling points, the reactivity, so much. So it's a very powerful technique out of just a very simple idea, making these Lewis dot structures. So visualization, though, kind of helps, and knowing the shape helps us predict the structure. This pretty much looks like, Emily, what molecule? Do you recognize it? H2O. Good. So we have the hydrogens, and then you have the oxygens. And you can't see the O too well, but you have these red parts and these blue parts, right? They're trying to illustrate what? Do you know, Lauren? What are they trying to illustrate? To me, it kind of starts out with this question, though. Is this supposed to be a covalent or an ionic type bonding is what they're trying to illustrate for water? Ionic if you see a what? Metal. There's no metal, right? So it must be covalent. So it's got to be that sharing idea, which is really kind of ambiguous. But the element that is the more, it's the E word, electronegative, it's going to hold on to the electrons more. They're going to hang out there more often. Nobody knows whose electrons are whose. They're all these valence electrons are just thrown in a pot, because it's the valence electrons that do everything, and they're not equally shared. So if you're more electronegative, they're going to hang out more often by the oxygen. So what is the exact shape of this water molecule? Does it actually look like this? No, it's probably more like a cloud is what it would be the best visualization. And that cloud is going to be more dense where that oxygen's hanging out. Because remember, these things are pretty much all empty space. It just got that extremely small core. Think of the atom, an orange on the 50-yard line of the Alamo Dome. That's your nucleus. The atom's the whole darn Alamo Dome. So this is all pretty much empty space stuff. Okay. Covalent bonding. We kind of we just kind of spoke about what covalent bonding is. But what types of atoms form covalent bonds? Megan, how would you answer that? Anything but what? Metals. Yeah, anything but metals. I just don't include them. So where is that on the periodic table? All right, quick periodic table. All right. Bowdy? On this periodic table, if you can identify it there, where are the nonmetals? The things that form covalent bonds? On the left?
Oh no, the right. I was totally thinking that.
Okay.
Sorry.
Yeah, over here. And it's the minority, right? It's the minority of the stuff. This stuff. Covalent bond formation. So we'll take a couple of these nonmetals. Kenneth, we took hydrogen here. And you have its valence electrons stuck on each atom. Forms a bond. And then we're going to illustrate, instead of doing all these dots, a lot of times they just do this. What's the octet rule? Octet rule. What's the octet rule? Someone was talking about the valence shell. The valence, you want 8 electrons. What's so special about 8, Sydney? Why 8? Yeah, it's when it's super stable, and just like who? The what gases? The noble gases. 8 valence electrons, right? Right here are nobles. 8 valence electrons, right there at the end of the periodic table. So, does it look like hydrogen obeys the octet rule, Giselle? Nope. Not even close, right? But it does obey, it meets the essence because it has the same number of valence electrons, Lorena, as what noble gas? Right? Here it doesn't. But now each hydrogen has how many valence electrons around it? 2. What noble gas has 2 valence electrons? What did you say? What noble gas has 2 valence electrons? Up here at the very corner? Helium. Helium has 2 valence electrons. So it's meeting the essence of the idea. But what we're getting into is not everything obeys the octet rule. So life isn't going to be as straightforward as we would like it. How about, and we'll see some of those coming up. Mia, when we start drawing these Lewis dot structures and for molecules, does this look like a single, double, or triple bond? Single, right? But there are such things as double and triple bonds. Okay, so we'll be drawing more than one line in there. Sydney, what's your feeling there between single, double, and triple bonds? Would these bonds be getting stronger? Yeah, I would say they'd be getting stronger too. Would they be getting, how about size-wise, Paul? These single, double, and triple bonds, right? If you had a triple bond in comparison to a single bond, I agree with Sydney that triple bond is going to be stronger. Would it also be shorter? Or would it be longer? Would it be longer? Or would it be the same? Yeah. Good question. Think of if it's tougher, stronger, it's more rigid, hard to bend, it's going to be shorter. It's going to be shorter. So things are getting tougher, more difficult to stretch. Only atoms. So we're not going to be forming these double and triple bonds with anything. You can form single bonds with all these nonmetals, but only double and triple bonds, Tanya, go with 3 elements. Yeah. It's somewhere in the reading. I don't know where. I don't know what page. All I remember is, I call it CNOS. So there they are. Carbon, nitrogen, oxygen, and sulfur. So it can be carbon-carbon. They can form a double or a triple bond. Or it could be carbon-nitrogen. It could be a form of double or triple bond. Just among those 4 is where you get the double and triple bonds. So don't be throwing double and triple bonds on anything. Okay, Dylan? Okay, now we're going to be forming these bonds, and we're going to say that some are polar, some are nonpolar. What does that mean? Alyssa, what does that mean? Here's some pictures. Well, where we started out was a good idea. Water, they call it a polar molecule because you have these HO bonds. Now, just looking at one of the bonds in water, it's a very polar bond because oxygen, which one is more electronegative? Oxygen. You remember the most electronegative element is what, Connor? What's the most electronegative element on the planet? F. So pretty much the idea is the closer you are to F, the more electronegative you are. That's all you really got to remember. Except don't include the nobles because they don't do jack. So oxygen is sitting there right next to fluorine, extremely electronegative. So you think you could write this to kind of indicate things, but this means something. Minus and plus, chemistry really comes down to math. When you write minus and plus, that means -1 and +1. That's for ionic compounds. No, this is talking about a sharing thing. So you have to write this little delta. What does the little delta mean? Manuel, what does the little delta mean? It means partial. So you're supposed to write partial negative, partial positive. And then, so So these are polar bonds in water. And then what's kind of interesting, I think, is if water wasn't bent, if water was like this, it would be nonpolar. Because these electronegativities, everything would kind of cancel out. But it's not, it's bent. So that really influences water big time. Water does some very strange things. For example, ice floats. There's no other solids. They don't float in their solution. They all sink. Water floats. Without that, lakes would freeze from the bottom up. There'd be no life. So there's a lot of very peculiar things with water. Okay. Sketch an arrow from the elements with the smallest to largest electronegativity. Steph, Connor kind of already answered this, but where would you draw from where to where? Yeah, from here all the way to which element? F. So pretty much F. All right. And then they gave you some ideas here. This is some more visualization. They're trying to say, okay, you have HH, okay, and they're trying to say that is completely nonpolar. And what they want you to think of as nonpolar is everything's green. There's no unequal sharing because they're identical atoms. They both have the same tug on the electrons. But when you make them different, make those atoms different, H and F, well, the electron's going to hang out by the more electronegative one. So you make it a little bit redder where the more electronegative element is. You make it bigger because the electrons are hanging out there more often. The cloud's bigger. Okay, and then the opposite end that's less electronegative. It's bluer. Think of it that way, or smaller. Okay, so this would be polar, the polar idea, and the nonpolar idea. Okay. Circle the bond below that is least polar. Dylan, we've got 1, 2, 3, 4 bonds there. And you're supposed to figure this out by comparing the electronegativities of the different elements. Yeah, I don't know if it's the same as yours or not.
It's like right there.
Oh, okay, it's kind of a little bit down. Which bond is the least polar? N. Everybody agree? Yeah, they're exactly the same. How about let's change it around. Which one is the most polar? Emily, how would you answer that one? Which one is the most polar? That might be a hard question. NCl. So you want to find two that are the farthest apart on the periodic table, right? I think maybe HN, right? Because they're the farthest apart. That would be my guess. But pretty much to answer the question, you got to find these tables. There's little numbers for electronegativity for every single element. Then you just subtract the two and see the biggest number. But for us, just look at the periodic table. That'll be good enough. We're not going to get that detailed on it. Indicate the partial charges for the bonds given below. So here's some bonds. Write the little partial plus and the partial minus where they belong. And then I'll ask you to see where you put them. So Lauren, how about the chlorine-fluorine bond? Jeez. Chlorine the negative one, and fluorine the... Everybody agree? Go on to the next one. Which one is more electronegative? Fluorine. So fluorine should have the... Yeah, fluorine should have the negative. Because nothing gets more electronegative than fluorine. How about HCl? What'd you do for that one, Megan? Good. And remember, you got to have those partial symbols. Otherwise, it's going to be wrong. How about number 3 here, Bowdy? Yes, you can't write anything. They perfectly cancel out. It's kind of a trick question. Okay. Rules for writing Lewis electron dot structures for molecules. So, let's see here. This is what we're getting at. Well, I say you have these rules. Now, there's a lot of real details to them, and you can read over them. I say we just jump into this, and then I'll go through the steps, and you can kind of go back to the other page and see where I'm at. Okay? So let's write some Lewis formulas for the following molecules or ions. So what you're supposed to do is the first element is what you're supposed to put in the middle. Now, there's only how many elements here in this molecule, Megan? There's only 2, so there's really nothing in the middle. But so you write them out, Br, Br. Okay. And Kenneth, in most cases, the real goal is to get how many electrons around each one? 8. And there's going to be some weird cases where it's not going to fit the octet rule, but that's the goal for pretty much everything. You try to get 8 electrons around everything. Now, when we talk about these electrons, Giselle, what electrons are we talking about? Starts with the V. The valence electrons. So you can only have how many, each dot is a valence electron, Lorena. So if we have a molecule, Br2, we better have only how many dots on that? No more and no less. I mean total. You count up all these dots, you better have only how many? Each bromine has how many valence electrons? Look at the periodic table!
7.
Each bromine has 7, so you better have a total of 14. So that's the next thing I do. I have to have a total of 14 valence electrons total. Okay. So, well, you know, might as well just start. This one there's not really a whole lot to do. All right, how many did I use up so far? 2, 4, 6. Used up 12. All right, and then I guess you can, but they don't want it to look like this. Do you see how I used up all 14? Each bond has how many electrons? Mia, each bond looks like it takes up how many electrons? A bond takes up, according to this, where's a bond? Okay, here's a bond in the middle. How many dots are there? 2. So each bond takes up, say it, 2. 2 electrons. All right, so did I use up all 14? Yeah. They don't want it, what I'm getting at is they don't want it to look like that. They want it to look like this. Okay, so a bond has 2 electrons, like Mia said. Okay, H2S. Now, you almost always take the first element and you're supposed to put it in the middle of this molecule. But H can never be in the middle because H can only, Sydney, have how many bonds? H can only, we kind of started with it. H can only take how many bonds? Where'd it go? Here it is. H can only take 1 bond. That's it. So you never put hydrogen in the center. So the H's are out front because this compound is a, starts with an A. Acid, right? Has 2 acidic hydrogens. Okay, so we just put S, and we don't know the shape, so we don't know if it's bent or linear or what. Just write them in there. How many valence electrons, Paul, do we have to work with here? I can't see that. Sulfur has 6. Each hydrogen has 1. So it'll be 8 total. All right. So Tanya, what would you do now?
Put 6 electrons.
I put 4, but You know, maybe what we should do is draw the what first. 'Cause you know it has to have bonds, right? You do the bonds first. Because you know it has to have bonds. Do I mess with double bonds? Is this a possibility for this? Emily, is this a possibility for this molecule? Double bonds? No, because it's not. What did we say? It's not C. It's not CNOS. So no double bonds, even though S is there. Okay. So I just used up how many? 4. I have 4 left. So put them on there. Is sulfur obeying the octet rule, Alyssa? Yeah, it is. 2, 4, 6, 8. Sulfur is obeying the octet rule. Hydrogen never does. Hydrogen's happy with 2. Okay, do IBr2 plus. I'm giving you the hardest one here. IBr2 plus. So which element goes in the center? Iodine. Iodine goes in the center. Doesn't matter where you put these bromines. We haven't figured out shape yet. We're getting there. Figure out the total number of valence. See what you can do to make octets around things. And remember, double bonds only go with CNOS. So how many valence electrons are you guys working with? Is it 20? Right? Is it 20 or is it 22? Or is it 21? Megan's pretty confident here. She says it's 20. Right? There's 21 total, but it's plus. So do you take one away or do you add one? Oh, okay. First plus, so that means take away, right? But it's, we're always lazy with this. Plus is really plus 1. So that means you only take 1 away. So your total should be, let's do it all. Your total would be 3 times 7 minus 1. 20 valence electrons is what you have to work with. Okay. So Connor, what'd you end up with?
The line to HBr.
Yeah, good. That's what I did. I would do first too. Fill it up. What do you mean?
Dots around all the betas.
How many?
6.
6. Yeah, because then you're done. You have 8, right?
And brackets.
Okay. Oh, you even got the bracket thing going. Do we use up them all? 8. We have 8 around this bromine. We have 8 around that bromine. So we only used up 16. Yeah, 2 on top and bottom. Okay. All right. So let's go to the boards and see how many of these we can knock out, and we can have a good weekend. Now the next one, D, is a linear molecule. So talk amongst each other, try to draw your answer out and see if you can agree with an answer. So make sure you make the molecule as HONO. H is attached to O, which is attached to N, which is attached to O. That's what it says, right? Follow the structure. Come on, you lazy people. Come on. Come on, come on, come on, come on, come on.
But
Get.
you have them. Oh, it's 4 plus 6. Hey. You see, I get chairs over here.
It's the only way to get you guys off of your behinds.
Chair? Off of my chair?
Do I have to go back there? Are you gonna make me go back there? Yeah, you gonna make me go back there? Whoa, you want to follow? You want to follow that skeleton? I gave you the hint. H-O-N-O. It's a straight line. So make sure you follow the skeleton for this acid. How many valence electrons did you guys come up with? Well, each oxygen has 6, right? And then nitrogen has 5, that's 17, plus 1 would be 18. So your final answer should have 18 valence electrons on there. And things like to obey the octet rule, except hydrogen, as far as we know so far.
No, it's not what I meant. That's not what I meant. Take off your equals sign. I meant put 1 back on and
You want to figure this out? See, did you use up all 18? Okay, now you try to get octets around everything. This hydrogen's happy. This O has 2, 4, 6, 8. He's happy. This nitrogen has 2, 4, 6, 7. So maybe move him over there, see what happens. Now he's happy, but he's not. So what could you do? Has anybody figured this one out? Okay, do you have 18?
Yeah.
2, 4, 6, 8, 10, 12, 14, 16, 18. Okay, so here's an answer. But does everything have an octet? Yeah, everything looks happy, except he doesn't have 8. Did anybody figure out an answer where you can get this thing to work? Do you use all 18?
Mm-hmm.
2, 4, 6, 8, 10, 12. And everything has an octet? 2, 4, 6, 8, 2, 4, 6, 8, 2, 4. I think there might be more than one possible answer. I think these guys have one answer up there. I'm going to copy it. Do you have a same? Let's see if you have the same answer as this one. All right. You need 18 total, and an octet around everything. This is a possible answer. I bet you there's more than one. Did you guys come up with a possible answer?
Yeah.
Oh, yeah, the same answer. I thought there might be another one. Yeah, except they like to have the dots together instead of separated. All right. So go on to the next one if you got this one. If you don't see why it's answered this way, just ask. Does this make sense? You have to have 18 total. So you've got 2, 4, 6. What is this? Double bond? Oh, it's a single bond. So this is where it starts. Just get 18 dots on there. But everything has to be connected. So 2, 4, 6, 8, 10, 12, 14, 16, 18. So you start with 18. And then you look through here, and you see if everything has 8 dots. So this O has 2, 4, 6, 8. Because remember, bonds are 2. So 2, 4, 6, 8. He's done. This one, 2, 4, 6, 8. He's done. This one is just short. So how do you get 8 around him and 8 around him? So you can't just, I wouldn't do this first. I would erase first and then move it over. And each bond is 2 electrons, so I just moved those over there. So then I didn't screw up my total. And now this O has 2, 4, 6, 8. Did I screw up this one? 2, 4, 6, no, I didn't. So that's the trick. And the only reason why I can do that is because of CNOS. That's the only time you can play that game, is between these elements. Okay. So remember, you can only play the double bond game between CNOS. Huh. Anybody get an answer for cyanide? What's the total?
Isn't she missing 2 electrons?
11.
The total is carbon is 4, nitrogen is 5,
So that's 9.
plus
So
1,
plus 1, so
10.
it's 10.
10 valence electrons. Hopefully you're working with 10 valence electrons for cyanide. Okay. So did you get this to work? No, so everybody wants 8. 2, 4, this has 6. So it's not going to work.
Well, that's what I'm saying. Like, we were trying to figure out.
So you got to keep messing with it.
No, I know, but what we were saying is, like, what I was saying is this counts as 2, 4, and then 6, and 8.
Yeah, so
right?
this nitrogen's happy. Nitrogen's happy with this. 2, 4, 6. Nitrogen's happy, but carbon's not.
But do you see my point?
I guess.
And
I know they're sharing.
then it kind of likes the dots together.
Well,
So that's how they like to do it.
sure.
But so carbon has 2, 4, 6. So you got to fix it. There's something still wrong. Did anybody figure out cyanide? What did you get? Remember, keep the dots together. Don't have lone dots. It doesn't like lone dots. They're always paired up. And it wants 10 total because you have a -1. Right? Because you have 4 plus 5 plus 1 because you have -1.
And where do we put that 1?
Well, you just add it, plus 1. So your total is going to be 10.
And here's where would I add that?
Well, no, you have to have 10 total. Doesn't matter. Who knows where that is? You just have to have 10 total. So 2, 4, 6, 8. Put another one there. 10. Now you've got 10. Now you want to see if everything obeyed the octet rule. Carbon has how many around it? 2, 4, 6. He's not happy. Nitrogen has 2, 4, 6, 8. Hey, nitrogen's happy. But this one isn't, so you got to keep working. See what else you can do.
You can't do more than a dozen.
Now,
If this one can only have 4, right?
no, it can't only have 4. They go to a pot of valence electrons. And out of that pot, you try to get everything to have 8 electrons around them.
Okay.
Carbon only contributes 4 is what you're trying to say. He only contributes 4 to the pot. Nitrogen contributes 5. And then there's an extra one because it's a -1 charge. So here's what you have in your pot. 10 valence electrons total. So around this thing, you should have 10 electrons. All you have is 4 right now. So whatever your answer is, you have to have 10 total electrons around here. Anybody get this one yet? Cyanide?
We could do a triple
2, 4, 6, 8. So carbon's happy. 2, 4, 6. Nitrogen's happy. Do we have enough? Do you have 10 electrons though?
Yes.
2, 4, 6, 8. Ah! Manuel got it. Did you guys get it? Yeah. You got it. Oh, you need your brackets though, with the -1. Did you get it, Dylan? But carbon's not happy. Carbon only has 6 electrons. For cyanide. Carbon only has 6 electrons. So, Manuel, what did you have? You had a triple bond. Then what'd you do? 2 on each. That works. All right? Because I have a total of 10. And I have 8 electrons around everything. And it's CNOS, so I can play with triple bonds. And I have to have my brackets with a -1. Okay. Try COBr2. Now, again, though, which element has to be in the center? The rules. It's the very first element. So carbon has to be in the center, and you surround it with everything else. So that's their convention. Their convention is you take that first element and you surround it by everything else. Surround it. You don't make lines. If it's going to be linear, they got to tell you. Kind of like I did here for HNO2. So you have to surround it with these guys. And then you got to count up the total. What's that?
For H, is that like considered surrounded?
H.
For N and D?
D.
For HNO2, the one we...
Oh, no, that's why surrounded, no, that's a straight line. And that's why I had to tell you, because there's no way you could tell by HNO2 that it's really HONO. There's no way you could tell. So I had to tell you that.
Okay, so when you don't tell us, we have to surround it by the first one?
Yes.
Okay.
Yes. Oh, and keep them paired up. Keep them paired up. Oh, hang on. Just erase those. Now you've got 8, 8, 8. All right? Well, no, she used up all 24. Here's 8 here, and 8 there. All right? Used up all 24. Okay, so here's your possible structure. Does everything obey the octet rule? Yeah, he doesn't. Okay, so what can you do?
Take away.
You want to make these double bond things, right? But remember, you can only make double bonds with C.
CNO.
CNOS.
So you can't do double bonds, right?
Look at it closer. There you go. So try a double bond there. Oh, whoa, whoa. See, you did a bad thing. So when you do this, always erase first and then do it. Otherwise, you screwed up your count. So you erase first. Now do it. See what I mean? Because you just moved these down here. Because if you draw the line first, it's so easy to screw up the count.
2, 4, 6, 8. I'm happy. 2,
Yeah?
4, 6, 8.
He's happy.
Okay.
Yeah? That's it then. Yeah, I got that.
1, 2, 3, 4.
Oh, hang on. This carbon, if with the triple bond, You got 2, 4, 6, 8, 10. That's too many for that carbon.
Told you.
But if you have a double bond, he's happy. Leave that lone pair there. Right? Now it works.
8, 2, 4, 6, 8.
Did you figure out COBR2? Yeah, that's what I got too. That's what folks are getting in the back. Good.
For the next one?
Let me write this in here so folks can see it. So here's a good answer for F, right? Cl F2 plus. So Cl has to be in the center, surrounded by two Fs, right? So the idea here is, remember, Cl has to be in the middle, surrounded by two Fs. Now that's chlorine. If there was an I, it had to be capitalized. So that's Cl. P2. So pp, count the total valence. You only have 2 electrons showing up there.
No, I was going to ask, is it 5 on both of them?
Yeah,
So, how do you do that?
try it.
Like, if you double
Did you guys get ClF2 plus? How did you get this one to work? Now this chlorine, though, he doesn't obey the octet rule. Did you use enough? How many electrons did you use up? How many you're supposed to use?
7 for fluorine.
Uh-huh. And then,
Supposed to be 7.
yeah, so you should have 21, oh, minus 1, 20 total.
So 20. 7, 7, 18. So 19, 20.
There you go. Now everybody's happy.
So you kind of disregard everything?
No.
Even chlorine.
No, see, I think what you did is you skipped the very first step. The very first step is getting your total and writing it down somewhere so that you can verify. If you don't have this total electrons in your answer, it's wrong. It has to be wrong. So you have to have that total in there. So that's why I start there. So for ClF2 plus, hopefully you came up with 20 valence electrons. All right, and you pretty much connect them. They got octets around the fluorines. And then you're left with 4 for the chlorine. And he's done. Okay. So have a good weekend. There's a few more for you to play with in the homework.